Hello and welcome. About 4 years ago, I purchased a certified sample of trinitite, analyzed it, and made a video. You can find the link in the description below. In it, I showed the presence of uranium, plutonium, americium, and a natural isotopic variation of molybdenum, and some fission product like cesium-137. I also attempted to calculate the age of the blast using nuclear forensic. I have just enough of the trinitite sample left for another round of analysis, and this time, I'd like to explore the higher actinides created in the explosion 78 years ago. For that, let's go back to Alamogordo, New Mexico in the early morning hours of July 16, 1945. At the top of a 100-foot tower, in a corrugated steel cabin, on an oak platform, sits a complicated mess of wire and instruments surrounding a large metal sphere. This device, nicknamed the Gadget, is the first nuclear weapon ever made and is being tested today. Inside, 5,000 pounds of high explosive surrounds an aluminum pusher, and inside of that, another metal sphere. This one, made of natural uranium, is the temper. Just like Russian dolls, it contains a grapefruit-sized chunk of warm exotic metal. The two hemisphere of plutonium-gallium alloy is coated with silver, and the 6.2 kilogram of metal hosts a neutron initiator made of a 10 curie polonium source and beryllium powder. This whole device cost about $2 billion in 1945. In a few seconds, a series of events will take place and change this quiet setting in humanity forever. Because explosions are fast, we need to slow down time to fully appreciate the next sequence of events. First, the high explosive is electrically set off, and a chemical explosion starts its journey inward. It takes about 100 microseconds for the shockwave to get from initiation to the aluminum pusher. 100 microseconds or 10,000 shakes. More on that later. This expanding shock waves meets the pusher, which smooth out any ripples for a uniform compression front. Now the temper, the pit, and the neutron initiator are beginning to implode. The pressure is climbing to 1 million atmosphere, or 1,000 times greater than the pressure at the bottom of the Mariana Trench, or the weight of a cargo ship resting on a penny. In normal condition, plutonium has a density of 19.8 grams per cubic centimeters. Under these pressures, its size went from a grapefruit to a ping pong ball, and its density is over 50 grams per cubic centimeters. This highly compressed state is helpful for 3 reasons. 1. The plutonium is now supercritical, meaning its volume to surface area ratio is large enough to keep most neutrons from escaping the core. 2. The neutron mean free path is shorter, so any free neutron has a higher probability to encounter a plutonium nucleus per unit of time. And 3. The temper can reflect more escaping neutron back to the core than it normally would at a lower density. And because of that, it offers more inertia for the explosion to overcome, keeping the pit's integrity for a little longer. We are now about 120 microseconds into the explosion, and the outside of the shot cab looks something like this. We can see the corrugated steel glowing in contrast with the frame of the cabin. With the neutron initiator release of the first few neutrons, the chain reaction starts. It takes 50 to 60 generations of fission to get 1 kilotons of explosive power. So the longer the core remains in this configuration, the more fission and neutron generation can take place, and the higher the yield. That's why the temper is so important. Each fission takes a certain time to happen. That time, 10 nanoseconds, is called a shake. Each fission releases between 2 and 3 neutrons on average, so if we assume minimum neutron loss, 100 generations would largely consume the entire 6 kilograms of plutonium. 6 kilograms of plutonium would have a yield well over 100 kilotons. Since Trinity's estimated yield puts it at a 20-ish kilotons, we know that only about 15% of all plutonium was consumed by fission. And we can estimate roughly 70 generations of fission took place before the complete disintegration of the core. 70 to the power 2 equals 2 times 10 to the power 21 fission, and even more neutrons. That number is very close to the Avogadro number. Let's keep that in mind for later. From the first fission to the last, 70 shakes is 700 nanoseconds. In reality, it's even faster, because the chain reaction did not start with a single neutron but many. At this point of the explosion, the outside of the cabin looks like this. X-rays are ionizing the air, and the explosion is starting to spread outward. Only 300 microseconds after pushing the button, the high explosives has taken 10 times longer to reach the core than the whole fission took to complete. In less than 100 nanoseconds, 20,000 tons of TNT equivalent power will be released. 20,000 tons is about 8.3 times 10 to the power of 16 joules. That much energy released in less than 100 nanoseconds is 8.3 times 10 to the power of 23 watts. To put this number in perspective, this is 1,000 times the world's energy consumption of 1 year, but released in the amount of time it takes light to travel 100 feet. As a side note, Trinity was a rather small bomb. It takes the human brain 100 milliseconds to register an event and shut the eyelid. In that time, the entire process can happen 500 times. Now let's go back to the Avogadro number from earlier. There is another situation found in nature where matter is exposed to such a heavy neutron bombardment: the inside of a supernova. Nucleosynthesis is the process by which heavy elements are created inside a star, and exploding nuclear weapons do generate similar conditions. Some elements and isotope would not exist without supernova. So starting from plutonium-239, we can safely assume that heavier element were also made during the explosion. In fact, Einsteinium and fermium were discovered in the mushroom cloud of the 1952 IV Mike test. Between plutonium-239 and lawrencium, element 103, there is 102 isotopes with masses over 239. Not knowing what to expect, this could seem like a daunting task. But after 78 years, we can immediately dismiss all the short-lived isotopes, and nothing above californium is worth searching for. Also, a lot of isotopes will have similar decay chain with the same daughter accumulating from different parents. For example, californium-248 will alpha decay to curium-244, and einsteinium-252 will alpha decay also to berkelium-248, then americium-244, and finally again, curium-244. So I narrowed down my list to these 15 isotopes. That way, I can cover all the masses from 239 to 251. I've added uranium-238 and 235 for isotopic ratio confirmation, and everyone's favorite element, neptunium. Of course, some isobaric interference are expected, since a lot of these isotopes in this part of the periodic table have several overlap. At first glance, the uranium isotopic ratio corresponds to the reported natural uranium used in the temper. Plutonium-239 is at a very detectable 10 parts per billion, and plutonium-240 at 2.3% indicate a very good weapon-grade plutonium. Americium-241 was detected with X-ray spectroscopy here. Neptunium did show up with a slight excess of Neptunium-237 over Neptunium-236, both in vanishingly small quantity and with low confidence factor. Looking at higher masses, mass 249, 250, and 251 are difficult to explain without curium, berkelium, and californium. The half-life of each element isotopes can help expose the culprit. For example, mass 249 is likely to be californium-249, because all other isotopes of mass 249 have either short or very short half-lives. Mass 250 is likely to be curium-250, because of its long half-life and because the decay daughter end up at mass 246, which we do pick up in small amount. To be accurate, californium-250 decays the same way, but because it starts with a shorter half-life, more isotope at mass 246 should have accumulated, and the data do not support that. Finally, mass 251 is probably californium-251 for the same reason. Now, mass 248 gives this very suspicious large hit, and I strongly suspected some interference with thorium and oxygen. 232 plus 16 equal 248. So I look for thorium and possible interference as well. Sand in general is known to contain some thorium, and the white sand of New Mexico are no exception. I detected about 100 parts per billion, or 0.1 ppm of thorium, which clearly produces interference at higher mass, and in particular mass 248. Knowing that, I could calculate the fraction of detected isotope not generated by thorium alone. The final results are in agreement with the predicted model for transuranium productions in extreme neutron environment. In 1964, Operation Whetstone included a 38 kiloton device codenamed PAR. Its aim was to identify transuranium element in the aftermath of the explosion. The results can be found in this paper, link in the description. It points out the diminishing yield of higher mass actinide and the odd and even number seesaw pattern in recovery. After so many years, my data can only show one of those two factors: less higher mass isotope and more lower masses. Just like with plutonium, in the first video, I can use uranium ionization potential and general behavior to estimate the concentration of these three elements in trinitite. Unfortunately, upper actinide's calibration standards are still unavailable to the public. To summarize, transuranium isotopes are definitely present in low part per billion and part per trillion range in trinitite, but their parent isotope could be higher on the periodic table. After 78 years, only the longer-lived daughter are still detectable. If you're thinking about collecting enough trinitite to separate some of these elements, consider this. To isolate a gram of plutonium, you'll need 100 tons of trinitite, 100,000 tons for curium-248, and over 1 million tons for californium. There is more iridium in your backyard. I'd like to pay a very special tribute to the radiochemistry pioneer who discovered and studied these elements. With limited resources, limited quantity, and hazardous conditions, they rearranged the periodic table, added a half dozens of new elements, and opened chemistry and physics to a brand new field.
Actually, one of the critical steps in the discovery of any element is its chemical identification. We must prove that it has chemical properties different from all previously known elements. Elution behavior in an ion exchange column can provide such proof.
Damn it!